This code imports libraries needed to work with stock data. It includes the Finance library for fetching data, NumPy for mathematical operations, pandas for data manipulation, and matplotlib for creating plots. The code also sets the plot style to seaborn-darkgrid for a more visually appealing display.
This code creates a list called tickers with the stock symbols for Apple, AAPL, S&P 500 ETT, SPY5 and Microsoft, MSFT. It combines these symbols into a single string separated by spaces and uses it to retrieve historical stock market data from these companies using the YF tickers method. The code then generates a data frame named History with the 10-year historical stock market data for these specific companies.
The code combines each column name in a data frame with an underscore to rename the columns. Then, it shows the first few rows of the data frame to display the updated column names.
This code retrieves the column names from a pandas data frame named History, using the columns attribute.
It then generates a list containing the names of the columns in the data frame. This code generates a figure with two adjacent subplots.
The first subplot contains line plots, showing the normalized historical closing prices of Apple, AAPL, S&P 500, and Microsoft, MSFT stocks.
The colors of the lines in the plot are defined using a custom color palette. In the second subplot, it shows the 30-day average volume data for 3 stocks using area plots with a custom color palette. Finally, a title is included in the figure to describe the data being shown.
This code uses the Yahoo Finance library to gather historical financial data for a list of stock tickers.
It arranges this data into a pandas data frame for further evaluation and visualization through matplotlib. The prepare_data function retrieves historical stock data for either multiple tickers or a single ticker during a specific time frame. Meanwhile, the plot_data function displays the chosen data column, such as closing prices for the selected tickers in a line graph. The prepare_data function receives a list of stock tickers and a chosen time period, then produces a data frame containing historical price data for those tickers. If multiple tickers are provided, the function merges the data into one data frame. The plot_data function, on the other hand, generates a line plot using the data frame created by prepare_data, enabling users to see the historical price trends of the chosen tickers visually.
This code is designed as a basic tool to retrieve, arrange, and display historical stock price data for the purpose of visualization and analysis. This code uses the NumPy library to create a 3D array with dimensions 2 by 2 by 2.
The array is populated with random values and not preset to any specific numbers. This code snippet initializes a 3 by 4 array with all elements set to 1. It's set to contain only integer datatype elements.
This code creates a 3 by 3 array containing random decimal numbers between 0 and 1. It utilizes the random module from NumPy to generate the matrix with 3 rows and 3 columns, populating each element with a random decimal value within the specified range.
This code creates a 3 by 3 array, filled with random numbers ranging from 0 to 1. It uses the np_random rand function from the NumPy library to generate the array with the desired dimensions and random values inside it. This code creates a 3D array filled with random numbers that have a normal distribution.
The numbers have an average of 3 and a spread of 4. The array is structured with 3 rows, 3 columns, and 2 layers.
Each value in the array is randomly generated according to the specified normal distribution parameters.
This code uses NumPy to create random integers.
The first line displays a random whole number from 0 to 9. The second line repeats the information from the first line, but it clarifies that the range is from 0 to 10. The code on the third line creates a 1D array containing 5 random integers between 0 and 9, and then prints those integers. The fourth line creates a 2 by 3 array containing random integers from 0 to 9, and then displays the array. This code generates a 3D NumPy array with random integers ranging from 0 to 100. Afterwards, it displays information about the array. The shape of an array displays the size of each dimension within the array. The number of dimensions of the array is a term that refers to the count of how many dimensions are present in an array. The number of elements in the array simply refers to the total count of elements present in the array. The data type of elements in an array indicates the type of data each element in the array holds. This code creates a 5 by 10 array with random integers from 0 to 10.
It then computes and displays different statistics about the array, like the total sum of all elements, sum of each row and column, maximum value in each row, minimum value in the entire array, and the average value of all elements. This code determines the position of the largest element in each row of an array by providing the index of the maximum value for each row. This code creates a function named manual_mean that calculates the average value of an array of numbers.
This code uses NumPy to create a random 1000 by 1000 array. After that, it computes the mean of the array using a custom function. The program then measures the time taken to calculate the mean by implementing a double for loop and prints out the time taken for this task. This code uses the NumPy library in Python to find the average of numbers in an array. It measures the time taken for this calculation by noting the start time, t1, and end time, t2, of the process. Finally, it displays the time it took to find the average using NumPy.
This code generates a 3 by 3 by 3 array, filled with random numbers between 0 and 1, using the np_random function from the NumPy library.
The print array statement shows the entire 3 by 3 by 3 array in the output.
The statement "array 00" accesses and prints the value at the first position of a three-dimensional array.
This code creates a 4 by 4 grid of random integer values between 0 and 9 using Python's NumPy library. It displays the full array and a specific subset of the array. The subset shown is made using slicing notation. The part before the colon, 0, 4 to 2, indicates that the subset starts from index 0, stops at index 4, not inclusive, and progresses by 2 steps.
This method picks every other row and column of the initial array, starting from the first row and first column. This code generates a list of stock symbols such as SPYs, AAPL, BTC-USD.
It then calls a function called prepare_data to collect data for these symbols and merges them into a data frame named df.
Finally, it shows the initial rows of the data frame using df head. This code generates a plot using data from a data frame df for specified tickers.
The plot's dimensions will be 10 by 5 units. It also provides a secondary y-axis for the close_BTC-USD and close_ETH-USD columns, making it simpler to compare these columns with the primary y-axis data. This code calculates different statistical values, like minimum, maximum, mean, median, and standard deviation for the close prices of stocks. It analyzes each stock in the given list of tickers within a data frame. This code utilizes financial information for the stock identified by the ticker symbol SPY. It generates a plot illustrating the stock's closing price alongside its 20-day rolling average.
Additionally, it displays Bollinger Bands, which are volatility bands positioned both above and below the stock's moving average. Bollinger Bands are used to determine whether a stock is overbought or oversold based on its current price level. The code processes data for the stock SPY plots, the closing price, and includes a 20-day rolling average.
It further computes upper and lower Bollinger Bands by adding and subtracting 2 standard deviations from the rolling mean respectively, which are shown as dashed lines on the graph. This code shows the stock price of SPY, along with its moving average and Bollinger Bands.
It helps to understand the stock's volatility and find possible trading chances. This code takes the closing prices of the SPY stock, S&P 500 ETF, and calculates the percentage change over time. It then creates a graph showing this percentage change in gray color.
The code also finds the mean of the percentage change and adds a horizontal line representing this average in maroon color on the graph. Additionally, it includes text on the plot to show the mean value with the specified format, font size, and position on the x-axis date.
This code calculates the daily percentage change in the SPY stock's close price and displays it on a graph.
It subtracts yesterday's price from today's price, divides the result by yesterday's price, and then subtracts 1 to get the percentage change. The graph helps to see how the stock price fluctuates daily.
This code compares the initial price of a stock with its current close_SPY price to calculate the percentage change, then displays this information on a graph.
This visualization helps to track how the stock price has fluctuated over time, relative to its starting value.
This code includes 3 functions organized within a class to analyze financial data.
The rolling_statistics function in Python computes rolling statistics, such as the mean for a specified column in a data frame. Additionally, it can create visualizations of the rolling statistics, including the option to include Bollinger Bands in the plot. The function find_returns evaluates the percentage change in a dataset over a set window, such as daily returns. It can also display this data graphically if chosen. The FinancialData class is a tool used for managing financial data. It comes with functions for organizing financial information, creating charts with Bollinger Bands, gathering statistics over time, and calculating returns for specified columns and tickers.
These functions and methods help with analyzing financial data, showing trends visually and calculating returns. They make it easier to understand and interpret financial information. This code performs the following tasks. A list is made with tickers such as SPY, BTC-USD, XY, NYB, and MCFT.
You can obtain historical financial data for specific stocks over a 5-year period by using the FinancialData class. Financial data is organized and prepared into a data frame. This function computes returns using the closing prices of selected tickers. It then generates a histogram plot of these returns, allowing customization of parameters like transparency, number of bins, and plot style. This code creates a histogram for a data frame called returns_df, showing how the data values are distributed. It uses bins of size 50, and the resulting histogram will be displayed in a plot that is 15 by 15 in size. The plot will have a title Return Distribution Close Price with a font size of 20 at the top, providing a visual representation of how returns are distributed in the data frame. This code analyzes the data in a data frame called returns_df by calculating 3 statistics for each column: mean value, standard deviation, amount of variation, and kurtosis, peakness or flatness of the distribution. This code examines how returns are distributed for a stock, denoted by the variable close_SPY.
The AGG function is used to calculate the average variance and shape of the returns in a dataset.
It generates a graph showing the distribution of returns using 30 bins and colored in maroon. Vertical lines are added to the histogram to show key values such as mean, standard deviation, 1.95 times the standard deviation, and their negative counterparts. This visual representation helps illustrate the distribution of returns. Afterward, text is included in the plot to display the mean, standard deviation, and kurtosis that have been calculated. The plot visually shows how the statistical analysis was done on the returns distribution of the stock, represented by close_SPY. This code generates a scatter plot displaying the relationship between the closing prices of the S&P 500 index, close_SPY, and the Bitcoin price, close_BTC-USD. Each point on the plot corresponds to the closing prices of both assets on a specific day. By examining the scatter plot, we can visually identify any potential correlations or trends between the prices of these two assets. This code creates a scatter matrix plot with the help of the Pandas library. The scatter matrix plot illustrates the connections between each pair of numerical columns in a data frame.
The scatter matrix plot is being created for the data frame called returns_df.
The command figsize equals 1515 adjusts the size of the plot to be 15 by 15 units. When diagonal equals hist is specified, each column in the plot will display a histogram in the diagonal. When using the color attribute with the value teal, you can adjust the color of markers in scatter plots and histograms to teal. When using hist_kwds equals bins 30 color teal, you can customize histograms by specifying the number of bins and the color of the bars.
When alpha is set to 0.2 in a scatter plot, it adjusts the transparency level of the markers.
When you run the code, a scatter matrix plot will appear. This plot will illustrate the connections between various columns within the returns_df data frame.
This code examines how the closing price of a stock market index, specifically the S&P 500 denoted as close_SPY, is related to the closing prices of other stocks.
To begin with, any rows in a data frame returns_df that contain only missing values are eliminated. The code identifies the list of stocks in the data frame except for close_SPY. A figure object is created for plotting with separate subplots made for each stock in the list. The code computes the beta and alpha values for each stock by performing a linear regression analysis between the closing prices of the stock and the close_SPY using NumPy's polyfit function. It creates a scatter plot that displays how the closing prices of a stock relate to the close_SPY variable, each on their own subplot. It shows the regression line on the scatter plot. Last, it includes text in each subplot, displaying the beta and alpha values of the linear regression model. This code shows and calculates how the closing prices of different stocks relate to the closing prices of the S&P 500 index in a straight line.
This code computes the Spearman correlation for the columns in a data frame named returns_df.
Spearman correlation evaluates how closely two variables are related based on a monotonic function.
This method is useful as it can account for both linear and nonlinear connections between the variables.
This code initializes the required libraries and configures the style for displaying financial data graphs. This line imports functions from a module named financial_data, which probably includes tools for managing and assessing financial information.
The line import Yfinance as YF is used to bring in the Yfinance library, enabling the retrieval of stock market information from Yahoo Finance.
When we write import NumPy as NP in Python, we are bringing in the NumPy library.
NumPy is used for handling arrays and matrices, especially when dealing with a lot of data or complex mathematical operations.
The line import pandas as PD is used to import the pandas library, a tool commonly used for data analysis and manipulation. The line import matplotlib as MLP imports the matplotlib library, which is used for creating plots in Python.
This line imports the pyplot module from matplotlib, allowing us to create plots using a MATLAB-like interface.
This line of code sets the style of the plots to seaborn-darkgrid, a visually attractive style, commonly used for displaying financial data.
This code gathers historical financial data for the stock symbols SPY, XOM, GOOG, and GLD spanning 5 years.
The data is then processed without filling any missing values. This code contains two functions that are used to calculate the normalized prices of individual stocks and the total value of a portfolio based on the weights assigned to each stock. The `normalize_prices function receives a data frame containing stock prices, start and end dates, a list of stock tickers, and a column name. This function normalizes the stock prices for the specified tickers within the chosen start and end dates. It achieves this by dividing each day's stock price by the price of the first day within the specified date range. The get_portfolio_values function calculates the total value of a portfolio based on input parameters like stock prices, dates, stock weights, tickers, and column name. It first normalizes the stock prices, and then computes the portfolio values by multiplying normalized prices with stock weights. It then sums these values to determine the total portfolio value for each day. These functions assist in evaluating and monitoring how a group of stocks in a portfolio are performing, using predetermined weights and price information. The code `fd.get_tickers is probably using a function or method called `get_tickers from an object or module named `. This code helps get a list of ticker symbols, which are short abbreviations that represent financial assets such as stocks, bonds, or options. This code calculates the weighted sum of stock prices that have been adjusted for differences in scale across the chosen date range.
The normalize_prices function adjusts the stock prices to a standard scale within a specified date range. The dataset called prices holds historical stock prices.
To get the tickers of stocks, you can use the command fd.get_tickers. Weights are used to calculate the weighted average of prices for different stocks. This involves multiplying the normalized prices by the specific weight assigned to each stock. The function .sum computes the weighted sum of the normalized prices.
This code is carrying out two main functions. This tool calculates the total value of a portfolio by using stock prices, date range, weight of each stock, and stock tickers.
It then shows this value over time through a graph for the specified date range.
It adjusts stock prices to a chosen date range for specific stock tickers and displays the adjusted prices in a graph.
These plots are commonly used to show and compare how a portfolio performs in terms of total value and the adjusted stock prices throughout a period of time.
The following code initializes a portfolio object by providing specific details such as ticker symbols, historical data duration, in this example, spanning 5 years, and the respective weights assigned to each ticker.
Each ticker denotes an individual asset within the portfolio, like stocks or commodities, while the weights determine the percentage allocation of each asset within the portfolio.
Essentially, this code establishes a structured portfolio based on the specified parameters for potential analysis or additional modifications.
This code imports key libraries for handling data and creating visualizations in Python. It includes pandas for data manipulation, NumPy for numerical operations, matplotting data for plotting data, and Sharpe for optimization tasks. It also configures the plot style of matplotlib to seaborn-darkgrid. This code creates a function called f that accepts an input x.
The function test_run is probably a function that runs a test.
Since it's not defined in the code provided, we don't know its exact function. It might be part of a testing framework or a custom function made for running a specific test case.
In general, when test_run is called, it should execute a test scenario and show the outcome, indicating if the test passed or failed. This code establishes a function named error that accepts two parameters, line and data.
The function calculates the error by summing the squared differences between the actual data points and the predicted values based on a linear equation. The function ultimately provides the error value, e, as its result. This code creates a function called fit_line that uses the least squares optimization method to fit a straight line to a set of data points. It requires two inputs, data x and y coordinates of data points, and error_func, a function to calculate the error between the fitted line and data points. The fit_line function starts by guessing the slope and intercept of a line, then plots this initial guess on a graph. It proceeds by using the minimize function from the SciPy library to calculate the best slope and intercept values that minimize the given error function. The test_run function creates a random line with a specific slope and intercept. It introduces noise to the generated data points, and then utilizes the fit_line function to determine the best fitting line for the noisy data.
This function plots the original line, the noisy data points, and the fitted line on a graph for visualization.
The code is showing how to best fit a straight line to data that has some noise by using a method called least squares optimization.
This code helps optimize a portfolio by focusing on the Sharpe ratio.
The get_Sharpe_ratio function computes the Sharpe ratio of a portfolio by subtracting the risk-free rate from the mean portfolio returns, and then dividing this difference by the standard deviation of portfolio returns.
This ratio is useful for assessing a portfolio's performance relative to the risk it carries.
The optimize_portfolio function is used to find the best weights for assets in a portfolio. It requires initial weights, returns of assets, and the risk-free rate as inputs. If no initial weights are given, it assumes equal weights for assets.
The function uses SciPy, optimize, minimize to calculate the optimal weights that maximize the Sharpe ratio.
The sum of weights must be 1, and each weight should be between 0 and 1. This code aims to determine the best weights for different assets in a portfolio in order to increase the Sharpe ratio. The Sharpe ratio helps to evaluate the return of an investment while considering the level of risk taken.
This code determines the weight for each column in the returns data, excluding the last column.
The weight for each column is calculated as 1 divided by the total number of columns except the last one. Subsequently, it uses these weights along with the returns data, excluding the last column, as inputs for a function called get_Sharpe_ratio.
This function presumably calculates the Sharpe ratio, a metric that assesses the risk-adjusted return of an investment.
This code creates a new data frame by selecting all columns from an existing data frame called returns, except for the last one. It achieves this by using the .lock method along with slicing operation. The code optimizes a portfolio's weight distribution to maximize its returns using historical returns of different assets. The function optimize_portfolio requires current asset weights, historical asset returns, and a risk-free rate as inputs to find the most profitable allocation of assets for the portfolio.
This code imports data from the financial_data file to be utilized within the current program.
By doing this, we can use functions, variables, or other elements that are defined in the financial_data module in our current script.
This code sets up a portfolio containing 4 assets: GOOG, Google, AAPL, Apple, and ExxonMobil.
Each asset is given an equal weight of 0.25 within the portfolio, meaning the total investment is evenly divided among the 4 assets. The portfolio is designed for a 5-year time frame.
This code is designed to optimize an investment portfolio using a mathematical algorithm.
The algorithm helps find the most advantageous mix of assets that offers the highest expected return, while keeping risk to a minimum.
By setting specific criteria or constraints, the code can adjust the allocation of assets in the portfolio to match the investor's objectives and constraints effectively.
This code displays 2 plots of a portfolio's data. The first plot shows how the total value of the portfolio shifts over time. The second plot illustrates how the prices of individual assets in the portfolio change in relation to each other, showing normalized prices over time.
The code is using the function get_Sharpe_ratio on the portfolio object to calculate the Sharpe ratio.
The Sharpe ratio assesses the return on an investment, considering its level of risk, providing insight into performance relative to risk.
This code generates a list named stds, and then proceeds to run a loop 10,000 times.
Within each iteration of the loop, it randomly selects between the numbers 1 and -1, with probabilities of 0.51 and 0.49 respectively, to form a collection of 1,000 values. The code then determines the standard deviation of these randomly selected values, and adds it to the stds list. Ultimately, it calculates and outputs the average of all the calculated standard deviations.